Cloud applications are growing fast, and with them, security demands are becoming more dynamic and complex. In the cloud, you cannot afford downtime, you cannot afford bottlenecks, and that's where Cisco Secure Firewall Virtual comes in. Hi, my name is Greeshma. I'm a technical marketing engineer at Cisco Systems. In this video, we'll explore Cisco Secure Firewall Threat Defense Virtual, focusing on clustering in AWS and also talk about cluster with autoscaling capability. We'll look at the architecture, key benefits for your cloud deployments, how deployment and configurations work, and much more. Let's get started. This is the agenda that we have for today. We'll start with a brief overview of Cisco Secure Firewall Threat Defense Virtual, in short FTDv, followed by a quick overview of clustering, then clustering with dynamic scaling capability, then talk about target failover. We'll then look into different use cases, architectures, and traffic flows. I'll be doing this video in parts. So this is all for part one. And part two, we'll be looking into how to deploy the cluster with dynamic scaling capability in AWS step by step. And we'll look into all the configurations needed and how target failover works, etc., in action. Okay, without further ado, let's get into the topic. To start with, what is Cisco Secure Firewall Threat Defense Virtual, right? It's a Cisco virtualized next generation firewall. It delivered security capabilities like advanced threat protection, intrusion detection and prevention, identity and access control, URL filtering, VPN, security intelligence, application visibility and control, etc. But in a fully virtual form factor that runs in the cloud or any virtualized environments. You can deploy FTDv in various public and private cloud providers like AWS, Azure, GCP, Oracle, VMware, KVM, etc. This makes it ideal for organizations moving applications and workloads into AWS or multi-cloud because it provides consistent enterprise-grade security no matter where your applications live. With FTDv, you get agility, scalability, and cloud-ready security without sacrificing control or visibility. And traditionally, organizations used to deploy standalone firewalls in the cloud. They work well for many cases. But as soon as the traffic volume grows or applications demand higher availability, standalone instances can quickly become a limitation. And this is where firewall clustering in cloud changes the game. Just like clustering in on-prem environments, clustering in the public cloud allows multiple FTDv instances to work together as a single logical firewall. That means they share state, and to share state across all the nodes in the cluster, we use something called as cluster control link, CCL in short. And within cluster, you can distribute traffic. Basically, I would say cluster acts as one highly available and scalable firewall system. Cluster provides all the conveniences of a single device while taking advantage of the increased throughput and redundancy you would expect from deploying multiple devices individually. As I mentioned, Cisco uses CCL for forwarding asymmetric traffic across devices in the cluster and uses VXLAN for CCL. And clusters can go up to 16 instances or nodes and now can span across multiple availability zones. But if someone asks why one will opt for clustering instead of just scaling standalone firewalls, right? Like, let's see a few of the reasons why people will choose cluster over normal standalone deployment. One of the reasons is resilience. For example, let's say if one firewall instance failed, others instantly take over with zero interruption to active sessions. And that's because of this particular feature called target failover in AWS. We'll be talking about it shortly. And from version 7.6 and above, FTDv clustering is also supporting multiple availability zones. So your cluster can span across multiple availability zones. And the other reason, one of the other reasons why people choose clustering is scaling. Cluster allows you to elastically scale out by adding more firewall nodes while still behaving like a single firewall, right? So that is one of the reasons. And the other one is efficiency. Instead of managing multiple independent firewalls, clustering reduces the complexity by centralizing policies and state information. And consistency, right? With shared state, sessions are preserved across the cluster, ensuring smooth user experience even during failover. So, clustering in cloud brings the same reliability and performance you would expect in the data center, but optimized for cloud scale deployments. And there is always another question, or I would say discussion, whether one should choose cluster or an autoscale solution for their cloud deployments, right? And that's a valid one, right? Both the solutions have their advantages and disadvantages. With cluster, as we discussed, all the firewalls in the cluster can share the state information. And with autoscaling, firewalls in the autoscaling group can scale up and scale down based on the metrics like CPU, memory, or health of the instance, etc. So you need to choose the solution based on your specific use cases. But now you don't need to worry about choosing one solution over another solution for your cloud deployments because Cisco is bringing together clustering and autoscaling in Secure Firewall Virtual. With clustering, as you all know, multiple firewall nodes operate as one logical unit, sharing state across all the nodes so traffic is distributed and failover is seamless. With this dynamic scaling capability, cluster can dynamically expand during traffic spikes and contract during quiet periods, ensuring both performance and cost efficiency. Together, they deliver resilient and elastic security in AWS with the simplicity of managing a single firewall. Clustering with dynamic scaling capability is supported from version 7.6 in AWS and from version 7.7 in Azure, and it will be supported in GCP from version 10.00. So now cluster has a capability of dynamic scaling. We'll see this in action while deploying the cluster in part two of this video. So, okay, let's quickly talk about the various roles of nodes and cluster and their responsibilities. Right? So here, if you see, we have a firewall cluster with three nodes and a client and a server. In a secure firewall cluster, each node plays a specific role to ensure reliable and stateful traffic handling. The owner is a node that first receives the connection. It maintains the TCP or UDP state and is responsible for processing the packets, right? So connection always has one owner, and if the owner fails, another node takes over and a new owner is selected seamlessly. To support this, we have the backup owner, which continuously syncs state information from the owner. If the owner goes down, the backup owner ensures the connection can continue without disruption. Next, we have the director. Its job is to answer the question who owns this connection, right? So when a new flow is created, the owner registers it with the director, and if a packets arrive at the wrong node, the node queries the director, which points it to the correct owner. There's only one director per connection, so and if the director fails, a new one is chosen. And finally, the forwarder is another node which handles the redirection. If it receives packets for a connection it doesn't own, then it asks the director who the owner is and then forwards those packets appropriately. Once it learns the path, it continues to redirect the future packets to the right node without additional lookups. Together, these roles, owner, backup owner, director, forwarder, allow the cluster to share state across nodes, provide failover without losing sessions, and distribute traffic efficiently. Okay, let's walk through step by step how a cluster handles a TCP handshake between client and a server. So, step one, the client sends a SYN packet. It lands on one of the nodes, which becomes the owner. The owner then creates the connection flow, encodes its identity into the SYN cookie, and forwards the SYN to the server, right? And in second step, the SYN reaches the server, and the server responds with a SYNAC, but this packet may arrive at a different firewall node or at the same node, but let's consider it arrive at a different node, right? This node now acts as a forwarder. Since the forwarder doesn't own the connection, it decodes the SYN cookie, learns the owner's identity, creates a forwarding flow, and passes the SYNAC to the owner. If this is a UDP connection, forwarder has to ask director who the owner is. But now, since this is a TCP connection, the forwarder forwards the packet to the owner. So now the packet reached owner, right? So now the owner updates the director with the connection state. The director records both the TCP state and the owner information and serves as a backup owner for resiliency. Finally, the owner forwards the SYNAC back to the client. So from this point on, any packet that hits the forwarder are redirected to the owner. If packets lands on any other node other than the forwarder right now, that particular node queries the director to discover the owner and builds the forwarding path. So this is how the connection will be established between the client and server. Okay, so at the very beginning of the video, I briefly mentioned about target failover, right? So now let's understand what it is. AWS introduced this feature called target failover in 2022 for its gateway load balancer. So it ensures that if a firewall node in the cluster becomes unavailable or unhealthy, traffic is automatically redirected to one of the healthy nodes without disruption, right? This provides seamless continuity and keeps your applications protected at all times and provides the high availability and resilience that you need. It's a built-in capability of AWS Gateway Load Balancers target group. You can configure this target failover to rebalance the traffic, right? So if you see this is like a toggle button, you need to if you enable this toggle button, it will rebalance the existing flows to another healthy nodes if the node that handled the connection fails. Now let's go ahead and understand different use cases, traffic flows, and look at the architectures of those. Right. So the one that you are seeing right now is a inbound traffic flow. This is how the architecture looks like for inbound traffic flow when the traffic is coming from internet to your applications inside the VPC. On the left side of the screen, if you see, we have the application VPC, or you can call it as a spoke VPC with subnets, instances, gateway load balancer, endpoint. On the right side, we have the security VPC where we have our firewall cluster deployed with 3 nodes and the gateway load balancer. Gateway load balancer will monitor the health of the firewalls and make sure to send the traffic to healthy instances only, right? So if you focus on the traffic flow here, when the traffic comes from the user on the internet to one of the instances in your application VPC or spoke VPC, it will hit the internet gateway first, and then from internet gateway it will go to gateway load balancer endpoint, and gateway load balancer endpoint will then send the traffic to gateway load balancer, and gateway load balancers forward it to one of the firewall nodes in the cluster, and firewall inspects the connection or the traffic, and based on the policies that you configured on the firewall, let's say assume firewall allowed the traffic, then it will go to the gateway load balancer again and to the gateway load balancer endpoint and then to application instance. So this is how the traffic flows when the traffic comes from internet to your applications inside the VPC, right? And what happens if the firewall node inspecting this specific traffic flow becomes unhealthy? Right? So with target failover configured, the gateway load balancer automatically redirects that flow to another available or a healthy node in the cluster. For example, as you can see here, node 2 was handling the traffic and it failed. The traffic is seamlessly forwarded to node 3, ensuring continuity without disruption. Now, this is another flow where east-west flow, where an instance in application subnet 1 is trying to reach an instance in application subnet 2 through the firewall. To make this work, the route tables are configured so the traffic from subnet 1 goes to the gateway load balancer endpoint, which forwards it to the gateway load balancer through AWS private link, and then to one of the firewalls in the cluster. And after inspection, the return traffic follows the same path back through the gateway load balancer and gateway load balancer endpoint, and finally to the instance that is in subnet 2, right? Again, here node 3 was handling the traffic. If node 3 fails and become unhealthy, the gateway load balancer automatically redirects the traffic to another healthy node in the cluster. In this case, node 2 is handling it, right? This is one another use case where you have multiple VPCs and you would like to protect the inter VPC traffic. In this architecture, if you see, we have two spoke VPCs and a security VPC hosting a firewall cluster, a transit gateway that is connecting all the VPCs through VPC attachments. And based on the route tables, traffic from spoke VPC 1 goes to the transit gateway, which forwards it to the gateway load balancer endpoint and to the gateway load balancer, and finally to one of the cluster nodes for inspection. After inspection, traffic returns through the same path: gateway load balancer endpoint, transit gateway before reaching the instance and spoke VPC2. And again, in case of failure, gateway load balancer will forward the traffic to another active node in the cluster, right? Another common use case is securing traffic between AWS VPCs and on-prem data center. In this setup, we have spoke VPCs and a security VPC in AWS. With the transit gateway connecting these VPCs, the data center connects to the AWS through either a VPN attachment or through a direct connect in AWS, right? Based on the route tables, traffic again from our VPC flows through the transit gateway load balancer endpoint, and to the gateway load balancer, and then to one of the firewall nodes for inspection. After inspection, the return traffic follows the reverse path, which will go through gateway load balancer endpoint, transit gateway before reaching the data center, right? In case of failover, the gateway load balancer will send the traffic to one of the healthy nodes in the cluster. And this is how the traffic flow works. Okay, these are all the different use cases or the traffic flows, and we saw how traffic flows in different scenarios. Okay, with that, let's wrap up the part one of the video. To summarize, we started with brief overview of FTDv, followed by clustering and why we need clustering, and clustering with dynamic scaling capability, and then followed by roles and responsibilities of various nodes in cluster. And then we discussed about target failover feature, and then we understand how traffic flows in different scenarios or the use cases. In part two, we'll dive into the deployment and configuration of the cluster in AWS. I don't want these videos to be lengthy, so we'll stop here for now. And I hope this was helpful. Thank you for watching and see you in the next part.